Hello everyone. So far we have discussed about the Gauss theorem and some examples of Gauss theorem. So today we will discuss few more situations in which Gauss theorem is very useful in calculating the electric field. So let's start it. Now we have discussed about the electric field due to a charged shell. Today we will take a sphere, and that is a non-conducting sphere. If I will take a conducting sphere and if we will provide a charge on this conductor, then we know that no charge can reside inside the conductor. So all the charge will transfer to the body of this sphere and it will behave just like a charged shell. So a charged conductor and a charged shell both are equivalent. Now, since I am dealing with a non-conducting sphere, it means the charge will be uniformly distributed on its entire volume. The radius of this sphere is r, and let me take the total charge on this sphere as q. So first of all we will find out the electric field at a point P that is lying outside this non-conducting charged sphere. So for that we know that to apply the Gauss theorem we need a Gaussian surface. So I am just taking a Gaussian surface of a radius small r, and that is spherical in nature, and we will take a small portion over here just like the previous questions. This area is ds, so area vector is normally outwards. For the positive charge, electric field will also be normally outwards, and these two, electric vector and the area vector, both are in the same direction. So I am going to apply Gauss theorem here, which states that the net flux through this Gaussian surface must be equal to the charge enclosed divided by epsilon naught. We can also write flux as E dot ds, charge enclosed divided by epsilon naught, and since these two are in the parallel direction, so I can write it as P ds cos 0 was Q enclosed divided by epsilon naught, and this is going to be, now the charge inside this Gaussian surface is the net charge on this non-conducting sphere, and that is Q. So I will write the enclosed charge as Q divided by epsilon naught. This is nothing but the area of this Gaussian surface which are having a radius of r. So this is going to be 4 pi r square divided by Q by epsilon naught. So this is, on simplifying, gives 1 by 4 pi epsilon naught Q by r square, and this electric field is exactly same as the electric field due to charged shell. It means whether I am having a charged shell or a non-conducting sphere with the same charge Q, then at the same distance the field will remain the same, and it behaves like that its whole charge is concentrated at its center. So if whole charge is at here, this point is at a distance of r, and it is the electric field due to a point charge. So we have seen that if there is a point outside the charged shell, conducting sphere or non-conducting sphere, the shell sphere behaves just like its whole charge is concentrated at its center, and this property may be utilized in solving the numerical problems. Now, if I will go on the surface of this non-conducting sphere, so I can simply write small r as the radius of this sphere, and this formula turns to this electric field is the maximum electric field that is on the surface of non-conducting sphere. Now, the interesting thing is a point that is inside this non-conducting sphere. Let me take the radius of this as r dash. Once again, to apply the Gauss theorem, we need a Gaussian surface, and we will follow the same procedure over here. So I am directly coming to this point. So we can write for this point inside closed integral E ds cos 0 as q enclosed divided by epsilon naught. This is now how we will find out the charge inside this Gaussian surface. So the concept of density is important here. So from the concept of density, first of all, if you will consider the entire non-conducting sphere, and let me charge its volume density as rho. So this is charge on the entire sphere divided by the volume of the sphere. We can also find out the density for this small Gaussian portion too, and let me take this charge as q naught, that is the charge inside this Gaussian surface, and the volume will be 4 by 3 pi r dash q, because r dash is the radius of my Gaussian surface. So if you will equate this, it is q dash equals to q by r q into r dash q. So I will use the value of q dash in this equation, and this is E. This is the surface area of my this Gaussian surface. This is 4 pi r dash square equals to, this is the charge q by r q multiplied by r dash q and 1 by epsilon naught. If you will simplify this on, it gives 1 by 4 pi, this is epsilon naught q by r q multiplied by r dash simply, and you will look at this term, this is a constant for this non-conducting surface. The electric field is directly proportional to r dash. It means if you are moving from the center toward the surface of this non-conducting sphere, the field increases as you go away from here, and here at the center, since r dash becomes 0, so at O, electric field will also be 0 since the value of r dash is 0. It means that the situation of non-conducting sphere is something different inside the sphere. Inside the sphere, field is only 0 at its center. It increases from center to the surface, and then it starts decreasing as per this equation. So I can draw the variation of this field like this. Suppose I am having a non-conducting sphere, and these are the boundaries, and this is the center O. So at center, the electric field is 0. If I will move from the center to the surface, the field increases, becomes maximum on the surface, and on going away it will decrease as 1 by r square as per this equation. Similarly, I can draw it for the left side too. So this is the graphical representation of electric field due to non-conducting charged sphere. So we have discussed the electric field due to non-conducting charged sphere. Now the Gauss theorem is very interesting in calculating, and it helps a lot to simplifying the calculations. So we are going to discuss one more numerical situation. Suppose that I just take a atom. So you know that in an atom there is a positively charged nucleus surrounded by the electron cloud. Let me take the radius of this cloud, or the radius of this orbital is r. So if the atomic number of this element is z, so the number of protons that will be inside the nucleus will be z, and the net charge will be plus of Ze. Now the exact amount of negative charge of minus Ze will be on this cloud. For simplicity, I am considering this cloud as a uniform. So it is a, you can say, mathematical atom where there is a positively charged nucleus surrounded by uniformly charged negative cloud so that the net charge on this atom is 0 and atom is electrically neutral. Now I am interested in finding the field at any point here inside this negative cloud. So let me take this radius as small r, and for better thing I can take this radius as a capital R. So to find out the electric field, we will apply the Gauss theorem, and here is my spherical Gaussian surface. If I will find out the flux from this Gaussian surface, it's simply enclosed charge divided by epsilon naught, and as per the previous situations we can write the flux as this is enclosed divided by epsilon naught. Now this is going to be ds. The important thing is how to calculate the charge that is inside this Gaussian surface. So first of all, I have made this nucleus of this size, but we know that practically it is a point sized. So just assume that it is a point sized. Now our job is to find out the negative charge that is in this cloud inside my Gaussian surface. So we will apply the concept of density here. So first of all, for this complete negative cloud, I can write the charge as minus Ze divided by volume, and the volume is 4 by 3 pi r cube. Similarly, I can find out the density from this portion too, and let me take that charge is enclosed charge, and divided by the volume will be 4 by 3 pi r cube. So from this equation we can find out the enclosed charge on this cloud only, and that comes out to be minus of Ze divided by r cube into small r. This is the charge that is enclosed in this cloud. Now since I am having a nucleus here also, and that contains a charge of plus Ze, so my net enclosed charge is the sum of the charge on the nucleus, that is plus of Ze, plus the charge on this electron cloud, and that is this one, so minus of Ze by r cube. So ultimately we can take Z as common, is going to be 1 minus r cube by small r cube. So this is the net enclosed charge inside this Gaussian surface, and here we need the net enclosed charge. So this is E, ds is surface area, that is 4 pi r square, just like the previous situations, and the enclosed charge is that one, that is Ze by epsilon naught 1 minus r cube by small. Now if you will simplify, you will get E equals 1 by 4 pi epsilon naught Ze by r square, and this is 1 minus r cube by r cube, and if I will introduce this r square inside this bracket, it will be 1 by 4 pi epsilon naught Ze in bracket 1 minus r square minus r divided by r cube. So this will be the electric field at any point inside this cloud. Now we will go on the surface of this atom. We know that if I will draw a Gaussian surface, then the net charge is going to be 0, as the whole charge on the electron cloud is minus Ze and the net charge on the nucleus is plus Ze. So since net charge is 0, it means electric field is 0 on the surface. And if we will go out from here, from this atom, once again the electric field will be 0, because for any point if you will draw a Gaussian surface, the net charge inside the Gaussian surface is 0, and if net charge inside the Gaussian surface is 0, it means there is no electric field. In electrostatics, we have learned that the electric field at every point within a conductor is 0, and that if there is any excess of charge inside a conductor, then the total charge resides only on its outer surface. But what if there is a cavity inside the conductor? So we will discuss this situation. Now, as I told you that if it is a conductor, then electric field is always 0 inside that conductor, and if I will provide some charge, the net charge will reside only on its outer surface. Now we will discuss what will happen if there is a cavity inside this conductor. So there is a cavity inside this conductor. Initially I am assuming that there is no charge on this conductor, but there is a cavity inside. Now since we know that electric field inside a conductor is always 0, so let us consider it is a Gaussian surface over here, and if electric field inside this conductor is 0, it means at this place also the electric field is 0, and if electric field is 0, it means that from Gaussian surface its field is 0, means the net charge inside that Gaussian surface must be 0, means there must be no charge inside this cavity, and it can be deducted from the Gauss theorem easily. Now I am taking another situation where there is a charge on the conductor and a cavity inside it. So in this situation also, as the electric field inside the conductor is 0, so if I will draw a Gaussian surface and my cavity is inside the Gaussian surface, since field is 0, it means the charge here must be equal to 0. Sometimes it happens that suppose I am having a charge of plus q that is placed inside the cavity. So what will happen in this situation? As we know that field inside the conductor is always 0, and if I will draw a Gaussian surface over here, there is a net charge inside this Gaussian surface. Now concept says that field inside the conductor must be 0, and it is only possible when the net charge inside this surface is 0, and to meet that condition we need an equal amount of negative charge inside this Gaussian surface, so that the net charge becomes 0 and the electric field is 0, and that meets the laws of electrostatic. So that situation, there will be an equal amount of negative charge that will appear on the inner surface of the cavity. Now since the net charge inside my system before introducing this charge was plus q, so my net charge for this system must be plus q. So to meet the law of conservation that we cannot produce a charge, we will take an equal amount of charge of plus q on the back side of this cavity. But this charge will not be here, since we know that no charge can reside inside the conductor. So what will happen? This charge will immediately flow and will appear on the outer surface of this conductor. So if we will place a charge inside the cavity, the same charge but in opposite polarity will appear on the surface of the cavity to fulfill the conditions of electrostatics, and it can be also derived from the Gauss theorem. and the same amount of charge will appear on the surface. And now you will see this is plus q, this is minus q, and this one is plus q. So the net charge plus q minus q plus q is plus q, especially on the whole system, and that tells that the net charge before introducing the charges was plus q, and after introducing the charge is plus q. Now the same situation can be there if I will take a negative charge inside the cavity. The positive charge will appear here, and the negative charge on the same amount will come on the surface of this conductor. What if my conductor initially have a charge? Let me take this charge, and this is a cavity. So my conductor is already having a charge, and that is on the outer surface of my conductor. There is a cavity, and I am going to add a positive charge inside this cavity. So just like the previous situation, to apply the Gauss theorem and to meet the conditions of electrostatics, the net charge inside this Gaussian surface must be 0, and to meet that condition we need to introduce an equal amount of charge but negative charge on the inner surface. Now the total charge inside this Gaussian surface is 0, means field is 0 here. Now to meet the conditions of conservation of charge, initially I was having a charge q, and I have introduced a plus q charge. So initially we were having plus q charge and this small plus q charge. So the equal amount of positive charge with small q sign will reappear on the surface, and the net charge on the outer surface will be q plus q. So if you will see the system, here the net charge is 0, and the total charge on the system is q plus q after introducing the charges to meet the conditions. Now consider a concept that I am having a uniform electric field over here. The magnitude of electric field is E. It means the magnitude of field is E everywhere in this area. Now what I need to do is I am going to place a conducting cell of rectangular shape inside this electric field. So if I will place a conducting box inside this electric field, so the situation cannot be same as you people are watching here, since the electric field lines in this situation is just crossing inside the conductor, and we know this is not possible. So we know that from electrostatics the field inside this conductor must be 0, and from the concept of the field due to charge cell, if it is a closed surface, then here also field must be 0. So what will happen, how these conditions will fulfill? So just let us consider this situation. This is a rectangular conducting box placed in field. Now what will happen, since we know that every conducting surface are having free electrons, so this electric field will apply a force on the free electrons in the opposite direction of the electric field, and these electrons, means the negative charge, will appear on this front surface of my rectangular shell. Similarly, as the charge is shifted here, a charge will appear on the other side of this rectangular slab. Now these are the induced charges, and they will produce a electric field exactly equal and opposite to my applied field, so that the net electric field inside this is 0. So my electric lines of force will modify and they will terminate here, at the edges it is not a corner type, it is something like this, as we know that field lines always terminates normal to the conducting surface. So the electric field lines will modify like this, so that net electric field inside the rectangular conductor and in the thickness of this electric conductor is 0. It means whenever you will place a conducting body inside electric field or in an electric field, the field lines modifies such that there is no electric field inside the conductor. Now we will consider a problem based on the facts that we have studied right now. So suppose I am having a hollow shell of inner radius A and outer radius B. The charge on this shell is capital Q, so that will reside on the surface. Now I am placing a plus Q of charge at the center of this hollow shell, and I need to find out, as per question, surface charge density of this surface. Let me call this surface as 1 and this surface as 2, and the electric field at a point P, that is at a distance of x, let us say. So as we have discussed the concept of cavity, as per the concept of cavity and to meet the electrostatics conditions, here the equal minus Q charge will appear and this plus Q charge will add up on the surface. So after introducing the induced charges, the situation will be like this. And if I want the surface charge density of surface 1, then you know that surface charge density is charge divided by surface area, and that surface area is going to be 4 pi a squared. It is the surface charge density of inner surface. Now if I will find out the surface charge density of the outer surface, then for outer surface the net charge on the outer surface is Q plus Q and the surface area is 4 pi b square. So these two are the surface charge densities of inner surface and outer surface. Now to find out the electric field here, I have told you that if you are having a point outside the cell, then cell behaves like its whole charge is concentrated at its center. So now I am having two cells, you can assume. The inner cell is having a charge of minus Q and the outer cell is having a charge of Q plus Q. So from the previous concept we can find out directly the electric field as 1 by 4 pi epsilon naught Q by R square. Here the distance is x. Now this charge is the total charge at this point O. So if you will place all the charges over here, you will get plus Q, this one charge, minus Q, plus this one charge, Q plus Q. So my net charge is simply Q plus Q, and that was initially on the outer surface. That's Q charge and this Q charge introduced by me. So the net charge of capital U plus small q will be effective at the center. So my total charge is Q plus small q divided by x square. So we can utilize the previous concept to find out the field at different locations.